Yes, and I will promote you and Zdeněk to co-hosts, which I'm not sure what the advantages are, but it's in case of some technical problems, I think it's always better to have more co-hosts. Shayan, can I start with the introduction already?
Sure, go ahead. Okay.
Yeah. So, hello everyone and welcome back to our second session at the Prague Summer School. It's my great pleasure to introduce Shayan Oveis Gharan from the University of Washington, and Shayan will be talking about using multivariate polynomials in algorithm designs in his lecture course. So please, Shayan.
Hello, thanks a lot, Jan, and all the organizers. It's a great pleasure to give these 5 lectures in this topic. So I hope you have taken a look at the website for the materials that I have posted. There are like 4 background lectures and 1 introductory video of what this area is about. One more thing. So there's also a link in the website to the notes that I'm writing down. So if you click on that notes, you can read these notes on a web page, and you can scroll up or down if you want to look back to what I've said before, like if you want to take another look at a definition or so on. So just a very 1 minute overview of what's going to happen. So we're going to have 5 lectures. In these lectures, I'm going to mostly focus on techniques and tools developed in this field, so-called geometry of polynomials, over the last maybe 1 or 2 decades. And I specifically try to motivate them and tell you about how these tools are used in different applications. So the first 2 lectures, I just introduced the tools. So lecture 1 will be about strong real stable polynomials and strong Rayleigh distributions. Lecture 2 will be about a technique called Gurwitz machinery and its applications. So these are basically introductory lectures in this field of multivariate polynomials called real estate polynomials. Lecture 3 is more sort of an application. We will talk about application to traveling salesman problem. Then lecture 4 will be about a different class of polynomials, multivariate polynomials, called completely log concave polynomials. And finally, the last lecture will be about application of this different class to problems about matroids. how can you count or sample bases or independent sets of a matrix. Okay, so let's get going. Let's start with our first lecture. And by the way, so I try to make all of these material sort of elementary. You should be able to understand them without that much of a background knowledge. Maybe I try to stop every, say, 20 minutes or so and ask if there are questions, so I can also tune my pace. So let's get started. So this lecture is about real estate polynomials. Let's get started by some definitions first. So we're going to work with multivariate polynomials. So I usually write P in R of Z1 up to Zn, for example, to say that you have a multivariate polynomial with real coefficients on n variables. Sometimes I write it's more than or equal to 0. This means that it has non-negative coefficients. If I do such a thing, so let me call this notation as opposed to definition. And so another definition, I say that a polynomial P in R of Z1 up to Zn is, say, D-homogeneous if basically P of alpha Z1 up to alpha Zn is equal to alpha to the D, P of Z1 up to Zn, for all alpha. Okay. So in other words, every monomial of P has a degree D. Another definition, and then two more. So I'm going to use this class H, this set H. It's a subset of complex plane. And basically, H is the set of points, let's say, in the complex plane, such that the imaginary value of C is positive. So this is the upper half of the complex plane. Now we get to the main definition of this lecture. We say a polynomial P with real coefficients on n variables is real stable if P has no root in the upper half complex plane. So if P of Z1 up to Zn is not equal to 0 whenever basically this point Z1 up to Zn is in H to the n. Okay, so if you choose any n points which have positive imaginary value, you don't get any root. Okay, so this is the first time I read this definition, it was probably 10 years ago that I got introduced to this field, and it seems a bizarre definition. Okay, what applications could it possibly have? It seems more sort of abstract definition, but hopefully towards the end of this lecture, we see some very tangible applications and examples of this. So just for now, let me try to give you a little bit of intuition. How can you think about this? So one way to think about this definition is to give you a different but equivalent definition. So an equivalent definition. Before that, let me tell you one more thing. So let me tell you one simple fact. If P in R of C, like a univariate polynomial, if it is real rooted, or let's remove the real, it's real rooted if and only if P is real stable. So this fact, basically, if you specialize it to the univariate polynomials, it's exactly the same as the real rootedness. And this is not hard to prove. Basically, it follows from the fact that the roots of a univariate polynomial come in conjugate pairs. If you have a root with negative imaginary value, you also get a root with positive imaginary value. That's something we proved in I proved in the these background notes. You can take a look. So basically, the point of this real stable polynomials is to have a definition that sort of generalizes real rootedness to multivariate polynomials. Okay, so that's something we want to see. So at least this, we did a sanity check that the univariate case makes sense. Now, let me tell you an equivalent definition. So P, let's say again you have a polynomial P in R of Z1 up to Zn. This polynomial is real stable if and only if for all A in Rn positive, if you choose any vector A with positive coordinates, and B in Rn, the univariate polynomial P of AT plus B, so this is a univariate polynomial, let's call it f of t. The univariate polynomial only in terms of this variable t. This is not identically zero and is real rooted. So how to think about this? What am I doing here? I have this multivariate polynomial, but the way I'm thinking about it is that I'm looking at it along a line pointing to a positive orthant. Okay, so I'm just looking at values of polynomial P along this line AT plus B. I just evaluate it. And I want that, I want that any such sort of one-dimensional restriction of P is real rooted and it's not identically zero. Okay, so I'm going to prove this. I'm going to prove that this is actually equivalent to the previous definition. But before that, let me show you one example, or maybe two examples. So look at this two polynomials. So the first one is the polynomial 1 minus z1, z2. And the second one is 1 plus z1, z2. These are not homogeneous polynomials. These are degree 2 polynomials in two variables. If you draw the roots of these polynomials, you basically get, for the left one, you get these roots. And for the second one, maybe could have, let me draw the roots actually in very blue. For the first one, it looks like this. Okay, so this is, so I'm drawing the space of, I'm drawing the roots of these polynomials in Rn. Okay, so even though in the first definition, I was evaluating the polynomial over the complex plane, now here, I'm just evaluating the polynomial over the real domain, R to the n. And I'm just, so these blue curves are just the space of the roots. Now, what I'm going to do is that I'm going to look at the roots of this polynomial along the lines pointing to the positive orthant. Now, you see there is this big difference between the first left picture and the right picture. In the left picture, every line pointing to the positive orthant will cross the roots at exactly 2 points. But in the right picture, there are some lines like this one that I just drew that cross the roots on at 2 points. And there are some other lines which cross the root at 0 points. So this means that the left polynomial is real rooted because it's degree 2. Every univariate restriction also is degree 2. It has exactly 2 points, so it is real rooted. But the right one is not real stable because there are some univariate restrictions like this one that if you restrict the polynomial along that line, you see no roots in the real domain, which means that the 2 roots will be in the complex domain. So the polynomial is not real root. Okay, so this is a test that the left polynomial in this picture is real stable and the right one is not real stable. Now, let me shortly prove this fact. So proof. So this is the if and only if. So you need 2 directions. So let's do the forward direction. So assume that P is real stable. I want to say that P of AT plus B is real rooted. Okay, so say by contradiction, suppose not. Then there exists T, which has imaginary value not equal to 0, such that actually I want to say it's real rooted and not identically 0. So there is T with non-zero imaginary value such that P of AT plus B is 0. So it has a complex root. Now, because this polynomial P has real coefficients, I can assume that the roots of it come in conjugate pairs. So I can assume imaginary value of T is positive. If it is not positive, I just take the conjugate of T, which has positive imaginary value. So now once I have that, I just define now define Zi to be AI T plus BI. Okay, for all I. Because T has positive imaginary value, I get that, sorry. I get that the imaginary value of Zi is positive for all I. But on the other hand, the polynomial is 0. P of Z1 up to Zn is equal to P of AT plus B is equal to 0, and that's a contradiction. The polynomial has a root in the upper half complex plane. Okay. So what did I show? I showed that if the polynomial P is real stable, then P of AT plus B must be real rooted. You can also check that it must be, it cannot be identically 0. I'm not going to do that, but you can also do the reverse direction. So reverse direction is now suppose P of AT plus B is not identically 0. And real rooted for all A positive and B in the real B in Rn. I want to argue that P is real stable. It's basically the same idea. So you say, again, you do proof by contradiction. So you do proof by contradiction. You assume that P is not real stable. That says that there exists, say, Z1 up to Zn in H to the N, such that P of Z1 up to Zn is 0. So what you do is that you just define AI to be equal to the imaginary value of Zi, and Bi to be the real value of Zi. and you get what you want. Okay, because zi's have positive imaginary value, ai's will be positive, and b's will just be real. Okay. So that was the proof of this this fact. So now we have two different ways to think about these real estate polynomials. One is that they have no roots in the upper half complex plane, and the second one is that if you look at any univariate restriction, the polynomial is real root. Okay, so now before going further, let me just do some examples and non-examples of these real estate polynomials. We already saw we already saw one example and one non-example. Here are some more. So one is this polynomial. If you look at a1 z1 plus a2 z2 plus an zn, where ai's are positive, this is a real stable polynomial. So this is a positive example. The proof of this, how to see that, it's that if you have zi's with positive imaginary value, it means that you can think about zi's as like vectors in the upper half complex plane, right? If they have positive imaginary value, they look like this. Now, when ai's are positive, I'm basically taking a convex combination of these vectors pointing to the positive, to the upper half complex plane. So if you have a set of vectors pointing to the upper half complex plane, you take a convex combination of them, still you get something pointing to the positive to the upper half complex plane, which is not zero. Okay. So if you take a convex combination of these guys, you get maybe something like this. So it has positive imaginary value still and cannot be zero. So this says that any linear polynomial, as long as it has positive coefficient, is real stable. And positive coefficient matters a lot here, because if it is not, then it's not. So a non-example is if you look at z1 minus z2, this is a real stable polynomial. Sorry, this is a linear polynomial, but it's not real stable. And why is that? You can set z1 equal to, let's say, I, the number with imaginary value of 1, and z1 equal z2 equal I, then the polynomial is 0, even though you have plugged in values with positive imaginary value. Okay, so this is a non-example. Another example is so-called elementary symmetric polynomial. So if you haven't seen this, I'm defining it here as well. So we write ek of z1 up to zn for this notation. This is a polynomial. It's a summation over all sets S, a subset of n choose k, or in n choose k. Every set S of exactly k of these variables. Now you take the product of I in S zi. Okay, so basically it has all possible monomials of degree k. Okay, and all of them have the same coefficient equal to 1. So this is a real stable polynomial. I'm not going to prove this one. It's an exercise that you're going to do after this lecture to prove that this polynomial is real stable. So let's see more. Another non-example is the polynomial z1 squared plus z2 squared. So this one is also non-real stable. You can just plug in, I mean, you can figure it out. It's like plug in maybe e to the I pi over 4 and I pi times 3/4, something like that. Okay, so this is also non-example. Okay, maybe here is a place to ask a question. Are there any questions at this moment? Okay. If you can also comment on the speed, if it is fast or so. Good. So now let me tell you a fundamental theorem, which is called some people call it mother of all stable polynomials, which is in general, how would you generate such a polynomial? I already told you some special cases like linear forms are okay, but is there some more generic way to construct real estate polynomial? And here is such a theorem. So let's say we're given PSD matrices, positive semi-definite matrices, A1 up to AN. In let's say they are D by D matrices, and a symmetric matrix B in Rn, sorry, in R of D by D. And we look at this polynomial, determinant of B plus summation of Zi AI. Think of it as basically this is P of Z1 up to Zn is this. Then this polynomial is real estate. Okay. So this says basically any set of PSD matrices and any matrix P, if you look at such a polynomial, you get a real estate polynomial. I'm not going to prove this. You can look at the proof in the notes. Due to time, I'm not going to prove it, but one thing I want you to remember is that it is well known. If you look at the notes, especially for the univariate case, you see that one of the natural examples of univariate real-rooted polynomials is the characteristic polynomial of a matrix. And you can sort of see such a theorem as a generalization of that fact, meaning that if instead of a univariate characteristic polynomial of a matrix, you look at the multivariate characteristic polynomial, which give you something like this, or maybe another example is that you can get with the same theorem is such a polynomial that you look at this matrix Z1 up to Zn on the diagonal, 0 everywhere else, minus A, and A is symmetric. This is another example. Remember, if I have Z on the diagonal, I have just one variable on the diagonal, I would have gotten exactly the characteristic polynomial. This would give you a multivariate characteristic polynomial. You can see by the same theorem that I've written here that such a polynomial is real estate. So in general, determinant-like polynomials that you get for symmetric matrices, like some sort of generalization of characteristic polynomial, are all real estate. So let me tell you immediately one application of this theorem. If you look at the notes, I've proved there in the background notes. In the second background notes is about random spanning tree distribution. So I proved there this so-called matrix 3 theorem. I proved the following fact, that if you have a graph G, you have an undirected graph G, you have these vectors BE for every edge E, where let's say if E is UV, BE is like indicator of U minus indicator of V. It's this vector which is a +1 on one endpoint, -1 on the other endpoint, and 0 everywhere else. Then you look at this polynomial, determinant of 1 transpose plus summation of say ZE, BE, BE transpose. This polynomial is exactly equal to summation of all spanning trees of the graph, product of E in T, ZE, maybe up to a factor of n squared. So maybe if I divide by 1/n squared, you get something like that. So up to a normalizing factor, these are the same thing. So the right polynomial, I'll say more about it. The right polynomial is called the generating polynomial of all spanning trees of the graph. And this matrix 3 theorem together with the theorem I said above says that the generating polynomial of all the spanning trees of a graph is a real estate polynomial. Okay, so this is generating of all spanning trees. And this is also real estate. Okay. Good. Now, let me tell you one. So one thing I learned from the works of Turing is that whenever you introduce a new concept, it's better you also immediately say or study its limitations. So what are limitations of these polynomials, or what class of objects can you possibly realize as a real estate polynomial? So there is this nice theorem of Coy, Oxley, Sokol, and Wagner. It's in 2006, or sorry, 2002. They proved the following thing: the support of any multi-affine homogeneous real stable polynomial correspond to basis of a matrix. So I haven't defined what I mean by multi-affine. Let me just, if you haven't, so we say a polynomial P is multi-affine. Basically, if it is a square, if every monomial is a square free. If every monomial is a square free, for example, say Z1, Z2 plus Z1, Z5 minus 2Z1. This is multi-affine, but Z1 squared Z2 minus 1 is not, because here I have a square, or say even maybe Z1 cubed Z1 cubed Z2 minus 1 is not, because it has a variable of degree more than 1. So multi-affine means that basically you don't have any square or cubes or whatever. Now, what does this theorem of Coy, Sokol, and Oxley Wagner say? It says that if you have a multi-affine homogeneous real estate polynomial, then the support meaning that the monomials which have non-zero coefficient correspond to basis of a matrix. Okay. So again, if you're not familiar with matroids, please take a look at this, the fourth, I think, background note I gave about matroids. So one example you see here immediately is that the spanning tree polynomial, the generating polynomial of all spanning tree, what is the support? The support is a set of spanning trees of a graph. This polynomial is multi-affine and homogeneous of degree n minus 1, and it's multi-affine, and the support corresponds to basis of a matrix. Another example is if you go above, is the elementary symmetric polynomial that we talked about. This is again a polynomial which is multi-affine and homogeneous. Here the support corresponds to basis of a uniform matroid of degree k. Uniform matroid is a matroid that you have all possible sets of a certain size. Now, what is a non-example? So a non-example is this polynomial. If you look at Z1, Z2, say plus Z3, Z4. This is a homogeneous multi-affine polynomial, but it's not basis of a matroid. If you look at 1, 2, and 3, 4, these two sets, I mean, this family of sets don't form a matroid. They don't form the basis of a matroid. They don't satisfy so-called the exchange property of the matroid. So what that means is that whatever coefficient I put here, It doesn't have to be 1. It can be any real number. For whatever coefficients I put here, I'm not going to get a real stable polynomial. Okay. So yeah, so this is the immediate limitation of this framework, that you cannot realize all possible, that you cannot realize any options. You can only hope to realize matroids. And furthermore, you cannot realize all matroids. I mean, I'm not going to spend time on it, but let me just say it informally, that not all matroids are realizable as support of real stable polynomial. So it's not true that if you have any matroid that exists a real stable polynomial with support equal to basis of that matroid. There are some matroids, like a Fano matroid, for example, that there is no real stable polynomial with support equal to the basis of that matroid. Okay, so in other words, if you have a real stable polynomial, it comes from a matroid. Real stable homogeneous multi-affine, it comes from a matroid, but not vice versa. It's not that from every matroid you can construct a real stable polynomial. Okay, good. Now, okay, so this was sort of the introduction. Now, sort of we have some rough idea of what these objects are. Now, I want to tell you about a very fundamental property of these objects called closure properties. So it turns out that this family of real stable polynomials have a very rich set of closure properties. They are closed under many, many operations. And this is very fundamental to their applications. Okay, so what I'm going to tell you now is a subset of their closure properties. And then in the next lecture, you will see a more generic set of closure properties. So let's say that we have a polynomial P with real coefficients, and let's say it's real stable. Then okay, then let's maybe also assume you have Q with the same property. Then the easiest thing is that the product of two real stable polynomial is real stable. This one is not hard to prove. Basically, the point is product of the roots of a product comes from the union of the roots. So if P and Q do not have any root in the upper half complex plane, so does the product. So product is also real stable. This one is the easiest to prove. The second one, maybe let's think about it. It's called symmetrization. So if you look at, let's say R equal P of Z1, comma Z1, comma Z3 up to Zn. Okay, so I symmetrize Z1 and Z2. I just, whenever I have Z1, Z2, I substitute with Z1. Call this new polynomial P. Sorry, this new polynomial R. The polynomial R is real stable. And the reason that the way to see that is that you just prove by contradiction. You say, suppose R is not real stable and it has a root in the positive, in the upper half complex plane. Look at whatever value you put for Z2, for Z1, put the same value for Z2 in P, and you get a root in the upper half complex plane. Okay. So they're closed under symmetrization. If P is real stable, so is R. Another one is called external field, or I should say positive external field. So let's say you have these vectors of lambda 1 up to lambda n, and they are positive. Then you define R of Z1 up to Zn to be P lambda 1 Z1 all the way to lambda n Zn. Okay, so this polynomial is also real stable. Again, you prove by contradiction. Suppose R is not real stable, it has a root in the positive upper half complex plane. Then let's say Z1 up to Zn are in upper half complex plane. I just multiply z1 with lambda 1, z2 with lambda 2, zn with lambda n, I get a root of p. And because lambda i's are positive, lambda 1 z1 also has a positive imaginary value, and so does lambda n times zn. So therefore, we get that p was not really stable to begin with, and that's a contradiction. Okay, so there are two more. Specialization. So here you define a polynomial R where you specialize a variable with a, sorry, let me. You define a new polynomial R where I specialize a variable with some number A, Z2 to Zn. So whenever I have Z1, I substitute it with A. So if A has a imaginary value which is non-negative, which is the other way around, wait a second. Sorry, non-negative, yes. If it has an imaginary value which is non-negative, then this polynomial R is real stable. So how to see that again? So it's very important it's non-negative. So first of all, if A has positive imaginary value, then of course, if R has a root in the upper half complex plane, it means that you can assign values to Z2 up to Zn in the upper half complex plane so that R is 0. Then to find a root for P, you just assign the same values to Z2 up to Zn, and you assign A to Z1. And because A has positive imaginary value, you're done. Now there's a special case of this, which is very important, which is the case when you assign a real value to A. So the point is, even if you assign a real number to Z1, if A is a real number, still there is no root. There is no root in the upper half complex plane. And the way to get that is a limiting argument. Okay, so basically, so in particular, if A is in Rn, in R, sorry, you get the real estate polynomial, and the reason is this: if you look at this sequence of polynomials pk, which are A plus, say, I over 2 to the k. I is again the real number, the complex number with imaginary value 1, comma Z2 up to Zn. Then, because any such thing has positive imaginary value, this polynomial is real stable. Now, pk converges to to R as k goes to infinity. As k goes to infinity, the imaginary value is 2 to the k converges to 0. So pk converges to the polynomial R, which has where you substitute Z1 with the real number. And because all of the polynomials here are real stable, so is the limit. And this in particular follows from the fact that the complement of this H is a closed set. Okay, remember H is the set of points with positive imaginary value. The complement of it is a closed set. So if you take the limit, this is fine. So in particular here, I'm using this other property, that limit of real stable polynomials is real stable. Okay, so far we have proven maybe 4 or 5 properties. They're closed under product, symmetrization, external field, specialization. The last 2 I'm not going to prove formally. You can just do it for yourself. So one of them is differentiation. If you look at partial P of, if you differentiate with respect to one variable, let's say Z1, you still get a real estate polynomial for any variable. This is fine. So they're closed under differentiation. And the second one is called inversion, which is the following. You, instead of Z1, you put -1 over Z1, and you use the same thing for the rest of the variables. Then you multiply it by Z1 to the degree of Z1. Okay, so you just do this to make this actually polynomial, and they're closed under this inversion as well. Okay, so if you look at the notes that I've written about real-rooted polynomials, you see that real-rooted polynomials are closed under many of the operations I just explained. Real-rooted polynomials are closed under differentiation, inversion, so on. So does the and so do these real-state polynomials. That is another reason you can think about these polynomials as a natural generalization of real-rootedness. Okay, so these are not all operations that these polynomials are closed under. There is a generic theorem I'm going to talk about in the next lecture, which tells you what under what operations or under what linear operations this family of polynomials are closed. But for now, let's just stick to this. Okay, so I have 15 more minutes. Maybe for a second, let me stop here. Is there any questions about what I've said so far, disclosure operations and so on? Okay, so if not, let's continue. So the last thing I want to say is a probabilistic analog of what I talked about called a strongly Rayleigh distribution. Sorry. Okay, sorry. So strongly Rayleigh distributions. So this is sort of a probabilistic analog of this family of real-estate polynomials. I need some definitions before talking about it. So let's say we have a probability distribution mu, which maps subsets of numbers. So that means, sorry, I'm going to use n to denote numbers 1 to n. And I have this distribution mu on subsets of 1 to n. The generating polynomial of mu is this polynomial g of mu, which is equal to, so it's a multivariate polynomial on variables z1 up to zn, and it's equal to expectation of z to the s for a set s sampled from mu. In other words, it's equal to summation of all sets, say subset of n, mu of s, probability of s under this distribution mu, times product of zi for I in S. Okay. By the way, I usually use, instead of this, I'm going to use this notation z to the S. This means that you take the product of zi for every element in S. So this is called a generating polynomial. And just to show you one example of what a generating polynomial is, say you have two independent Bernoullis. Let's say B1 and B2. And let's say this one has a success probability P1, B2 has a success probability P2. Then generating polynomial of B1, B2 looks like this. It's with probability P1 times P2, you get both. So you get P1, P2 times Z1, Z2. Then with probability P1 times 1 minus P2, you get B1 but not B2. So this is Z1 plus P2 times 1 minus P1 of Z2. With the probability P2 times 1 minus P1, you get just the second one. And with probability 1 minus P1, 1 minus P2, you get none. Okay, so this is the generating polynomial of this. Another way you can think about this is that you can rewrite the same polynomial as this. It's P1 Z1 plus 1 minus P1 plus P2 Z2. Sorry, this is times 1 minus P2. Okay, so how did I come up with this? The point is, each of these objects, this is the generating polynomial of B1. And whenever you have two independent random variables or two independent distribution, like a distribution made up of two independent, say, little objects, you can just take the product of the generating polynomial. Now, because P1 and P2 are between 0 and 1, each of these polynomials here is real stable. It's a linear polynomial. So, and the product of real stable polynomial is also real stable. So this whole thing I have for two independent Bernoulli is a real stable polynomial. Okay. And in fact, 2 was not special. You could just make 2 into any n independent Bernoullis with arbitrary success probabilities, and the generating polynomial would have been would be a real stable polynomial. Now, in general, we say this distribution mu is a strong Rayleigh if G of mu is real stable. Okay, and you just solve one example of such a thing. If you have any n independent Bernoulli random variables, they form a strong Rayleigh distribution. Now, here is a nice application of the set of closure property of real stable polynomials that we talked about. It turns out that basically many of the operations that you would do on a probability distribution can be naturally translated on operation on a polynomial. So let's start with it. So start with conditioning. Let's say you want to condition I to be in. Okay, so you want to condition some element I to be in your distribution. Then, so in other words, write it as mu conditional I. Then the generating polynomial of mu conditional I is nothing but you take the partial zi of g mu, and then you multiply it by zi. When you take partial zi of g mu, basically you're throwing off every monomial which doesn't have zi. You only keep those that have zi. But then you have to multiply zi back because you want to look at the generating polynomial of this new object. So you have to multiply zi back. Now, remember we said that real stable polynomials are closed under differentiation and product. So this says that this polynomial is real stable. There's one caveat that you may get confused about. You may think that I need to multiply basically the right-hand side by 1 over probability of I. That's true. I have to write down G of mu condition I really correctly. I have to rescale it by 1 over probability of I. But the thing is, under scaling, like scaling doesn't change the roots of a polynomial. So if you multiply a polynomial by 10, 100, a million, the roots do not change. So it doesn't matter. Okay, if you like, you multiply the right-hand side by 1 over probability of I. That doesn't change the root. So in other words, G of mu conditional I is still strong, right? Another operation is conditioning out. I out. So you condition on I bar, right? You condition on not having element I. What is this? What does this do to a polynomial? It's exactly equal to G of mu, where you set zi equal to 0. So you kill off every monomial that do have zi. You kill all of them off. You only keep monomials that do not have zi. And again, we said that by specializing a real estate polynomial to a real number, you still get a real estate polynomial. So again, strong Rayleigh distributions are closed under such a thing as well. So they're closed under conditioning in or out. Let me say two other operations. One of them is called projection. So let's say you fix say some set T subset of n, and you want to project your distribution onto T. So what does it mean? It means that, so I use this notation, you project onto T, it means that mu T of A, so if you have a set A subset of T, the probability of A under this projection is exactly equal to summation of every set S, such that S intersection T is equal to A mu of S. In other words, what does projection mean? It means that, okay, I have this huge probability distribution on a large set of large set of elements. I just zoom in, look at a specific set. I say, I don't care about the rest of the guys. I just care about this particular set. I just zoom in and just look at this. And I look at my distribution projected onto this. So for every possible subset here, I just average out everything outside and I see the distribution I get to this subset. So this operation is called projection. And the claim is that the strong Rayleigh distributions are closed on the projection. So the reason for this is that projection is exactly the same as G mu, where you set Zi equal to 1 for all I not in the set T. Okay, you just substitute 1 for every variable which doesn't belong to the set T, which is not in T, which doesn't belong to the set T, and you'll get the corresponding generating polynomial of the projected distribution. And last one is external field. This is sort of more straightforward. So if you have a distribution mu, let's define, and let's say lambda is this vector, like positive vector. You define mu star lambda. This is the distribution where for every set S, probability of it after this external field is exactly mu of S times lambda to the S. You just rescale every set by these sort of weights that you assign to elements. Okay, good. So now we know about this strong Rayleigh distribution. Now I want to end this lecture with some application of this machinery. In the next lecture, we'll see more application, but here this is just an introductory lecture. I want to say some immediate application. So let's say we have a graph G. It's an undirected graph, and let's look at mu to be the uniform distribution over spanning trees of G. Then G of mu is exactly equal to 1 over number of spanning trees, summation over all T, all spanning tree T of Z to the T. Now we already said that the generating polynomial of spanning trees is real stable, and by renormalization, you don't change anything. So this distribution, this polynomial is real stable. So G mu, so mu is a strong Rayleigh. So if you look at the uniform distribution over all spanning trees of a graph, you get a real stable polynomial. You get a strong Rayleigh distribution and the corresponding generating polynomial is real stable. Now here is a cool fact you can get from this. Say F is a subset of edges of the graph. Then I want to look at the law of my distribution over F. So let's say define AI to be the probability that T intersection F. So let's say I sample a spanning tree T from my distribution mu, and I want to say what's the probability that the intersection has exactly I edges. Okay, so AI says this. Now I look at this sequence A1 up to A of maybe A0 up to A of F. It's a probability to have 0 edges in F, 1 edges in F, 2 edges in F, all the way to have all of edges in F. This sequence correspond to sum of independent Bernoullis. So that's the lemma. How would you prove this? The proof basically just follows from what we talked about. You start with G mu, the generating polynomial of all of the uniform distribution over spanning trees of my graph. That's a real estate polynomial. Now I want to get to that set F. So first, project onto F. Okay, let's define maybe G1 to be G mu, where you set ZE equal to 1 for all E not in the set F. So first you project onto set F, and that's a real estate polynomial. Then you define G2 to be G1 of say T, comma T, comma T. So you symmetrize. You also said real estate polynomials are closed under symmetrization. You symmetrize, you get this univariate polynomial, and it's still real stable. But G2 must be real rooted, because any univariate real estate polynomial is real rooted. That's what we started this lecture with. Now you have this, now what G2 really looks like. G2 is really A0 plus A1 T plus all the way to AF T to the F. Remember, AI is where the probability that you get exactly I edges in the set F. And you can just check that the coefficient of T to the I is exactly AI in this polynomial G2. Now, G2 is real rooted. If you look at this background notes, I proved there that if you have a univariate polynomial which is real rooted, it has non-negative coefficient, it corresponds to sum of Bernoullis. Okay, I don't have time to prove it here. So basically, from the notes, from background notes, we get that there exist Bernoulli, independent Bernoullis. Let's say B1 up to B of F, such that AI is equal to the probability that B1 plus all the way to B of F is equal to R. In other words, you can write these coefficients, the rank, so-called the rank sequence of your distribution projected onto F as sum of independent Bernoullis. Okay, so this is a very, I mean, the proof of this is really simple.
Sorry, I'm now lost. So let me take F to be all the edges surrounding one vertex.
Mm-hmm.
In particular, you know that A0 must be 0 because whatever spanning tree.
Yeah.
But
so that says that one of the Bernoullis will have success probability 1.
Okay.
So the success probability of these Bernoullis can be anything. They don't have to be the same. They can be anything. Mm-hmm. And in fact, the success probabilities come from the roots of this polynomial G2 that I'm explaining here.
Okay, thanks.
Okay. Now this fact is very, I mean, it has a lot of consequences. So for example, you can talk about, I mean, all of the properties of real rooted polynomial that I talked about in this background notes can be used here. You can say that the sequence A0 up to AF is so-called unimodal, it is log concave, so such and such. So in particular, there is this very nice fact that you can talk about now. You can study what is the probability that T intersection F is even, for example. And that's a very fundamental, this is a different type of probabilistic statements that you would normally study in probability theory. You would normally study what is the concentration bound, what's the probability that I'm close to the expectation. But let's say here, for example, I know that the expectation is 1, okay? Suppose that So suppose that the expected value of T intersection F is, say, for example, 1. What is the probability that you get, let's say maybe odd here. What is the probability that you get odd number of edges in T intersection F? Okay, so one way is to say that you are concentrated around 1, but that buys you a little bit, but it doesn't buy you a lot. If you want to say that I want to be T intersection F equal to 1 and not 0 or 2, that's one thing. But more generally, let's say you're interested in the parity, which is a much different object, and you can actually study such a quantity and prove much stronger bounds as opposed to when you study concentration around 1. And these facts, I mean, I'll say more about it when we get to lectures on TSP, but these are crucially used, sorry. These are crucially used, okay, crucially used in TSP applications. Because in TSP applications, you're normally interested on the parity of set of edges sampled from, a subset. This set F can be, some crazy set of edges in the graph comes from the application, but you're interested in the parity of the number of edges of spanning tree sampled from the subset. And now using these machineries, you can study such a thing. Okay, so we're out of time. Let me stop here, and I'm happy if you have questions, happy to answer. Otherwise, we'll continue in the next lecture. Again, remember that my notes are available online. You should be able to access it in this link that I sent in the course website. Take a look. Let me know if you have questions.
Yes. So thank you, Shayan, for beautiful lecture. And yes, as I said in Subhash's lecture, everything is recorded, so you can, if you need to go back to watch something on YouTube, you can do so. Shayan has this Scribbly application, so you will find a link for that on our webpage, and he has lecture notes which you can find there as well. So thank you, and let's meet tomorrow at the same time.
Perfect. Thanks a lot.